Okay, in this chapter what we will be discussing is going to be ions and molecular compounds. So the very first question states as such: state the number of electrons that must be lost by atoms of each of the following to achieve a noble gas electron arrangement. All right, so first one is going to be chlorine. Now if you look at where chlorine is on the periodic table, it's going to be in the group 7, just before the very last group. The very last group happens to be called the noble gases. The noble gases are called noble gases because they do not do anything. And the reason they do not do anything is that their orbitals, their electron orbitals, are completely and entirely full. Now, what is it going to have to take, or how many electrons will each one of these elements that I'll read off is required in order to get to that noble gas? Well, chlorine happens to have 7 valence electrons. Remember, the valence electrons are going to be the outermost electrons. And so in order for chlorine to have a noble gas arrangement, it's going to have to lose 7 valence electrons. Thus, this becomes the answer for all the questions in this particular problem. But we'll march through each and every one. So since chlorine is in the group 7, which is called the halogens, it has to lose 7 of its valence electrons in order to have a noble gas arrangement. All right, so the very next one is going to be selenium. So selenium is in the 6th column. That's going to have oxygen on top, and selenium will be below oxygen, and thus it has 6 valence electrons, and thus it's going to have to lose all 6 of those valence electrons in order to have a noble gas arrangement. All right, to save time, I won't erase. The next one is going to be nitrogen. And so nitrogen is going to be just to the left of oxygen. It's going to be in the 5th group, and so it's going to have to lose 5 of its valence electrons in order to have a noble gas arrangement. And the last one in this problem is going to be sulfur. Right? And sulfur is going to be right below oxygen, right above selenium, and so it's likewise going to have to lose 6 of its valence electrons. All right. So this is a pretty easy problem, not too bad. We'll do a few more problems. So you get familiar. The main idea of this chapter, or one of the big ideas of this chapter, is that you become familiar with using the periodic table, particularly those columns. Molecules or atoms are placed in the columns that have similar chemical characteristics. And so oxygen and sulfur will have similar characteristics because they're in the exact same column. Same thing as the halogens, the alkali metals, the alkaline metals, they're all going to have similar chemical characteristics. All right, this problem states write the symbol or the ion of each of the following. So we happen to have fluorine. So fluorine. So we want to write the symbol or the ion for each. Well, fluorine is going to be in halogens, and so the symbol for fluorine is F, and as the ion, it's going to be -1 because it's going to gain 1 electron. Thus, why the negative sign? That negative sign does not mean that it loses an electron. It actually means that it gains an electron. So if it gains that 1 electron, it will now have a noble gas configuration in which its entire octet will be completely full. It will go from 7 to 8 by gaining that 1 electron. All right. The next one is going to be calcium. Now, calcium is a metal, all right, so it's not going to lose electrons. It's not going to gain electrons. It's going to lose electrons. And how this works at the nonmetals, such as fluorine that we just got done seeing, will gain electrons in order to get that full octet. Metals, which would be on the left-hand side of the periodic table, would much rather give up electrons. If it gives up an electron, remember electron is going to be negative, it will become a positive ion, which is referred to as a cation. So this one asks us to look at calcium. All right, calcium is going to be in the 2nd group. its symbol is going to be Ca. Since it's a metal, it's going to give up electrons. If it gives up electrons, it will become a positive charge. Since it's in the second group, it will give up 2 electrons, and thus it will be calcium 2 plus cation. All right. Next one we have is going to be sodium. All right, sodium is going to be an alkali metal, and it's going to be in the very first column. Okay, so if we write sodium, its symbol is going to be Na, because its Latin name for it is natrium, so thus it's given Na. It's in the first column, so it will give up 1 electron. So its symbol will be Na plus 1. All right. And now for the very last one in this problem, which is iodine. All right. So iodine, it's going to be in the halogens. It will be in the 7th column. Its symbol is I. Since it's in that 7th column, it will gain 1 electron, and thus it will have a -1 charge. Not too bad, pretty easy. But once again, I want you to become very familiar with this periodic table. It's an amazing tool. It's absolutely it's invaluable to chemistry because it organizes all these elements into their chemical characteristics. All right. The next problem says write the correct ionic formula for the compound formed between each of the following pairs of ions. So the first one is going to be between aluminum, that's going to be 3 plus, and chlorine. Now, typically what we do is we're going to write the cation first. The cation is going to be represented by what's positive, and it's going to be usually the metal. All right, so we'll write the metal first. That's going to be aluminum. Now, if you notice, it's going to have a charge of +3. The chlorine is going to be the anion. It's going to be the non-metal, and it just happens to have a charge of -1. So you have to ask yourself, how many of these chlorines are going to be required to make this a neutral species? Well, if this is +3, this is -1, you're going to have 3 chlorines to balance out the +3 charge here. So this happens to be called aluminum chloride, and it's going to be AlCl3. And once again, the reason is because the aluminum is a +3 charge, and the chlorine is going to be a -1 charge. Now, another way to look at this to make sure you get that number right, it works most of the time, but not always. It should work most of the time for this class, is if you have Al3 plus Cl -1, what you can do is, in order to get this subscript accurate, is you can take this 3, bring it down here, take the 1, bring it down here, such that the symbol becomes now Al. We typically leave the 1 off. Cl, the 3 goes down, and it becomes 3. For the most part, that works. There are some interesting compounds that deal with the transition metals, which we won't talk about in this class. That method does not always work. All right. So that's the first one. And the whole idea of this is to remember that you want to have neutral species. These molecules are going to be neutral. They are not going to be charged, all right? So they're going to be neutral. And so you want to make sure that the cations and the anions, that you get the proper number of them such that the charge cancels out, or you get neutrality, all right? B is going to be calcium and sulfur. So B is going to be calcium. It's a symbol 2 plus, and then sulfur 2 minus. Now this is a pretty easy one because you have something that's a +2 and something that's a -2, so just putting them together 1 to 1 is going to give you a neutral species. So this becomes calcium sulfide. So 1 calcium and 1 sulfur. All right, works out pretty well. Those are sort of nice and kind of easy. But these are going to be inorganic molecules. These are going to be ionic. For the most part, they're very easy to identify because you're going to have a metal bonded with a non-metal. And as I stated before, you typically write, or by convention, you write the cation, which is going to be the metal first, and then you'll write the anion second, which will be the non-metal. C is going to be lithium and sulfur. This is going to be +1. This is going to be -2. Once again, here what you have is you have a cation that's going to be a +1. You have a sulfur that's going to be a -2. If you want to do the old trick again, you just drop the 2 down here. You drop the 1 down there. And what you end up getting now is you get lithium 2, sulfur 1. And that's because this lithium has a +1 charge. This sulfur has a -2 charge. And the idea is that this entire portion of the molecule is 2+, all right? This portion of the molecule is 2-. If you add up 2+ and 2-, you're going to get a charge of 0, and that's the whole idea of this, all right? So I'm trying to show you different ways on how to solve these problems, all right? They're not too bad. Just make sure the whole idea is that you want to add the numbers up such that you can get a charge equal to 0, all right? A charge equal to 0. D, what does D say? D is going to be rubidium and phosphorus. So D is going to be rubidium, that's going to be +1, and phosphorus, which is 3-. So once again, we can move some charges. We can put this goes here, that's going to go there, and what we end up getting is going to be rubidium 3, phosphorus 1. And that's what the 3 indicates. I wasn't necessarily clear on that in the beginning, but this 3 indicates that there's going to be 3 rubidiums for every 1 phosphorus. All right. Once again, this charge here now, since we have the 3 rubidiums, is going to be a +3. We have 1 phosphorus. This charge is going to be a 3-. So this portion of the molecule is 3-. This portion of the molecule is going to be 3+. All right. And then the last one for this problem here. Hopefully you're getting the hang of these. If you don't, feel free to email me or contact me somehow, and we'll work through it. It's not too bad. Just very simple arithmetic is really all it is. It's nothing more than that. Please do not make it any harder than it is. So E, is going to be cesium. This happens to be +1, and iodine, which is going to be a -1. Once again, a really nice, easy one to do because the cation and the anion have the exact same charge, just opposite. And so this is going to be 1 cesium and 1 iodine. This is going to be a +1 charge. This will be a -1 charge. So that one works out pretty slick and easy. Not too bad. All right, that ends that problem. We got a few more yet in this chapter. All right, here we have to draw the Lewis dot structures. All right, so we need to draw Lewis dot structure somewhere. There's my notes right there. I usually have some notes so I don't mess this up. I do a lot of the recording late at night when my family is sleeping. It works out pretty well that way. So in this case, what we want to do is we want to draw, they're called electron dot formulas for each of the following molecules. I'll refer to them as Lewis dot structures. They were generated, invented, created by a physical chemist named Gilbert Lewis, and thus they're typically called Lewis dot structures. So we'll go through these. So we want to draw the electron dot formula for each of the following. So we have nitrogen triiodide. And what we're going to do is we're going to pick the metal that's, typically the metal that's written first is going to be the central metal. We'll look at nitrogen. I'll use some different colored markers. We'll use some different colored markers for the dots here. So we're going to start with nitrogen. All right, let's start with nitrogen. And if you look on the periodic table, it's going to be in the 5th column, so it's going to have 5 valence electrons as such. All right. If we do each iodine, all right, iodine is going to have 7. All right, so it's going to have 7. And so each iodine is in the 7th column. It's going to have 7 valence electrons. 3 times 7 is going to be 21 plus the 5, so we should come up with 26 electrons in our entire molecule. All right, that's ultimately what we want to do. So we have 26 electrons in our molecule. So this is nitrogen. It's going to have the 5. Then we start with an iodine here. So there's 1 electron. 2, 3, 4, 5, 6, 7. We do another iodine. That's just one of them. There's 1, 2, 3, 4, 5, 6, 7. So now I have 2 iodines. We'll have to do the third iodine. 1, 2, 3, 4, 5, 6, 7. Excuse me. So now what we have is we have a nitrogen and our 3 iodines. Now what we want to do is we want to make sure we have 26 valence electrons. So if we look, there's going to be 8 electrons here, 8 electrons there, 8 electrons there. 3 times 8 is going to be 24, plus 2 more gives us our 26 valence electrons. Excuse me, please. It's always nice to confirm that we have the right number of electrons when we're doing this. All right. And remember, those elements are in those columns, and they have similar chemical characteristics because they have similar number of valence electrons. Those valence electrons are the electrons that participate in the bonding. So the numbers of them are very important. All right? That's going to determine whether they're going to accept electrons or they're going to give up their valence electrons based on the number of electrons that they have. The next one is going to be carbon tetrachloride. So that's going to be CCl4. All right. So carbon has 4 valence electrons. Each chlorine is going to have 7 valence electrons. So 4 times 7 is going to be 28. 4 times 7 is going to be 28. Plus the 4 should give us 32 electrons. All right. We're going to start with the carbon. Carbon has 4 valence electrons. It's written first. We're going to start with carbon. So there's 1, 2, 3, 4. There's carbon's 4 valence electrons. Now we'll do the chlorine. There's 1 for chlorine. Make that out a little bit bigger. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. There's 1, 2, 3, 4, 5, 6, 7. Now there we've put all the chlorines in. We have all 4. Now the last step we want to do is count the valence electrons. So here's going to be 8. There's going to be 8. That's going to be 16. 3 times 8 is going to be 24. 8 more is now going to give us our 32 valence electrons. So it works out really well. We did not lose any electrons. All the electrons are going to be accounted for. And so this is how these molecules bond in nature at this level. All right. Get that nice and clean. We'll do a couple more. And so the next one is going to be chlorine. So there's chlorine gas. Each one is going to have 7 electrons. So we have to come up with 14 electrons. So here's a chlorine. All right, we'll give it 1, 2, 3, 4, 5, 6, 7. We'll draw the other chlorine. We'll draw it a different color. Really, one chlorine is the same as another chlorine, such that they have the same number of neutrons. There's 1, 2, 3, 4, 5, 6, 7. So if we count the valence electrons, we should have 14. Oops, forgot to write my E in there. But we should have 2, 4, 6, 8, 10, 12, 14. It's going to be 14 valence electrons. One thing I failed to mention is these pair of electrons here, these are going to be the bonding. Those are going to be bonding electrons. All right. The remaining electrons, well, I'm circling in pink, Those are going to be non-bonding. Oops. Those would be non-bonding electrons. All right. Sometimes this molecule, though, let me go back. This pair of electrons, this bonding pair of electrons, does not necessarily have to be represented as two bonds. You could very clearly draw this as the following. Sorry, let me get this erased. We can draw this molecule as such. As such, to save some time. All right. And we have just one more. Yeah, we have just one more in this problem, and we'll move on to something else. These Lewis dot structures, I think, are sort of enjoyable to work with. It's kind of like putting a puzzle together. From them, you also get to know the shape of the molecule. That helps to assist in giving the shape of the molecule. That will be important as we move on through this journey of general organic biochemistry. All right. And so here, it's going to be silicon trifluoride. All right. So silicon is going to have 4 electrons. The fluorine is going to have 7 each, so we're going to have 28 electrons. So there should be 32 total electrons that we have to account for. So if we start with our silicon, excuse me, and we put the 4 electrons around it, then we can now fill in the sulfur, or the fluorine, sorry. So there's 1, 2, 3, 4, 5, 6, 7. Have another one there. Have another one here. Pretty exciting watching me draw dots, isn't it? Sorry. There. Now we can count for all the electrons. Go through, do that. So here's going to be 8. There's 8. That's going to be 16. Another 8 is going to be 24. And then there we have another 8, which is going to give us 32 electrons. All right, let's see what else we have to do. A couple more problems in this chapter, and then we'll move on to the next chapter. All right. Now these can get fairly complicated for some of you who are going to go further into chemistry. These Lewis dot structures could be a little bit more complicated. They aren't always necessarily this simple. I don't mean to say that presumptuously that these are simple, but they, comparatively speaking to other Lewis dot structures, these are fairly simple ones to do. There are some complicated ones. The Lewis dot structures for the polyatomics is not necessarily straightforward. In order to do those successfully, you have to do what's called a formal charge calculation, which is not a difficult thing to do, but it's a calculation that will help you ensure that you get the correct Lewis dot structure. And as I said, that Lewis dot structure is important because it helps lead you to what the shape of the molecule is. And that will help you to determine whether the molecule is going to be polar or non-polar. And we'll get into that later as we go further into other chapters. All right. All right. Talking about polarity, that's where this problem is going to end up. We're going to be looking at some of these chemical bonds to determine whether they're going to be polar or not. So this question states, predict whether each of the following bonds is polar, is going to be non-polar covalent, polar covalent, or going to be ionic. So we want to determine whether they're going to be non-polar covalent. Typically, those are going to be reserved for homonuclear. There are going to be some heteronuclear bonds in which they are going to be non-polar covalent. The big primary one that really sticks out is going to be the carbon-hydrogen bond. But anyway, we'll go through and work through some of these. So the first one is going to be a silicon-oxygen bond. We want to determine whether this is going to be a non-polar covalent, polar covalent, or ionic. Now, the covalent ones are typically going to be between metal and non-metals. The ionic ones. The ionic bonds are going to be between metals and non-metals. The covalent bonds are going to be between non-metals and non-metals. So let me repeat that in case there's any confusion. The ionic bonds are going to occur between metals and non-metals. The covalent bonds are going to occur between non-metals and non-metals, all right? So silicon, since that's basically a metalloid, we'll treat that as though it's a non-metal. And so in this case, this is going to be a polar covalent bond. Let me finish that E there a little bit. All right. Next one is going to be potassium chloride. Potassium is a metal. Chloride is going to be a non-metal. So this is going to be ionic. All right. We'll do the next one. The next one is going to be sulfur fluoride. So if we look at sulfur fluoride, sulfur is going to be a non-metal. Fluoride is going to be a non-metal. Since it's not homonuclear, it's actually heteronuclear, this is going to be polar covalent. All right. Now let's see, the next one is going to be a phosphorus bromine. So we have phosphorus and bromine. Once again, we have a non-metal, heteronuclear, different nuclei. And so this will be a polar covalent bond. We just got a couple more. We'll use green. We haven't used green in a while. And this is going to be a lithium oxygen. And this is going to be ionic because you have a metal and a non-metal. And last but not least, we're going to have a nitrogen and sulfur bond. And once again, this is going to be non-metal. All right. Difference in what's called electronegativity. I'll talk about that in a few minutes. So this becomes a polar covalent. Sorry, I can't spell covalent. Now I'll give you a covalent one just to let you know. You could look at a carbon-carbon would be considered what is called a non-polar covalent. Sorry. So this would be a non-polar covalent. Now, what determines whether something's going to be polar covalent, ionic, non-polar covalent? Well, that is going to depend upon what's called the difference in electronegativity. So you look at the difference in electronegativity between the two atoms that are going to be bonded to one another. Difference in or electronegativity, recall from what the book says and what I've lectured about in the PowerPoints, is it's going to be the ability to, within a molecule, to attract electrons to itself. So if two atoms such as potassium and chloride have a very large difference in electronegativity, that's going to be ionic. If the electronegativity difference is not going to be super great, then that would be a polar covalent bond. And if there is no difference in electronegativity, you're going to have a non-polar covalent bond. The covalent bond, or covalent, simply means a sharing. If you have a non-polar covalent bond, that means there's equal sharing with the bonded electrons. If you happen to have a polar covalent bond, that means that this bonding pair of electrons is not equally shared. It's going to favor one atom over another. So the silicon oxide one's a real easy one. Oxygen is going to have a very large electronegativity, so it really wants this bonding pair of electrons. So it's going to pull that bonding pair of electrons towards the oxygen, making the oxygen here partially negative, all right? And the silicon is going to be partially positive because this pair of electrons is going to be pulled more towards the oxygen. Thus, it is a polar molecule. Just imagine the poles of a magnet. You'll have a north pole and you'll have a south pole. And thus the reason why it's called a polar covalent bond. Because that bonding pair is shared. It's just going to be shared unequally. It would be pulled towards, the bonding pair will be more pulled towards one of the atoms that's participating in the bonding. I typically sort of think of it as as an atomic tug of war. It's kind of what I think of it as one of those atoms in the molecule or in the bond really wants that pair of electrons. It's just a lot stronger and larger and bigger, and so it's going to pull that bonding pair of electrons more towards itself. But anyway, but the heart of what all this is it's going to be the electronegativity. And that's going to become important when we start talking about these biomolecules, which are going to be for the most part, fairly nonpolar. Then how are they ever going to exist in an aqueous environment, such as water, which is what the body mostly consists of, is a lot of water. And so this will be, how do these molecules, how do they exist, how do they function in this aqueous environment? All right, so the last problem for this chapter is identify the major types of attractive forces between the particles in each of the following. So the first one is going to be HCl, right? This molecule is going to be drawn as HCl. This is going to be a polar covalent bonded molecule, such that the chlorine is going to be partially negative. All right, the hydrogen is going to be partially positive. If we happen to have another HCl molecule here, and I'll just draw it in here as such, partially negative, this will be partially positive. What is going to happen is there's going to be an attraction between the negative chlorine and the positive hydrogen of another molecule. And this is what's referred to as hydrogen bonding. So hydrogen bonding is going to occur for this molecule. All right. The next one, B, this is going to be magnesium fluoride. All right. This happens to be a metal and a non-metal, so the interaction between this one is going to be ionic. All right. Next one is going to be C. This is going to be a phosphorus tribromide. All right. This is going to be a metal and a non-metal. All right, a metal and a non-metal. And this will be a more generic type of hydrogen bonding. Hydrogen bonding is a very specific type, which is internal electric force, which is referred to as a dipole-dipole, and that's what we have here. Since this has a hydrogen, this is referred to as hydrogen bonding. You could also call this dipole-dipole, and there would be nothing wrong with that. But the interaction here is going to be a dipole-dipole. If you draw this molecule out, you have one phosphorus, you have three bromines, and you end up having a pair of electrons here. And so there's going to be a positive portion to this, and there's going to be a negative portion to this molecule. And so one part of the molecule is going to be positive, another part of the molecule is going to be negative. They will attract themselves because they're going to be polar molecules. And so this will be a dipole-dipole attraction. All right. Just one more problem in this chapter, and then we'll be done with this chapter. But it's really interesting how these molecules can be attracted to one another as such. And it works a lot like, very similar to what occurs with magnets, right? If you ever go play with magnets, you notice that one end of a magnet will be attracted to another end of a magnet, and likewise one end of that magnet will be repelled by the other end of that magnet, of a different magnet or of a separate magnet. And these molecules behave in the exact same way, except instead of being magnetic forces, they are electrostatic forces in nature, such that you have something that's going to be positive and you have something that's going to be negative. And opposites are going to attract. The opposites are going to attract, such that the negative end of one molecule is going to be attracted to a positive end of another molecule. So the last one in this problem, D, is going to be ammonia. Since this is going to be a polar molecule and you happen to have hydrogen here, this is going to be hydrogen bonding. And what that's going to look like is you're going to have a nitrogen with three hydrogens as such. All right. These three hydrogens are going to be partially positive, this nitrogen is going to be partially negative. If we happen to have another NH3 here, what happens is that the hydrogen is attracted to that nitrogen, because this is going to be partially negative, that's going to be partially positive. And so there's going to be an attraction here, and that attraction is what's called hydrogen bonding. All right. If you happen to have any questions you have on this chapter, feel free to contact me either through email or some other way through the website. I'd be glad to answer any of those questions. Have a good day.